Okay, let's dive right into this. I want you to picture the most chaotic, intense, industrial environment you can possibly imagine. We are talking thick clouds of welding sparks, billowing smoke, iron shavings flying everywhere, and just absolutely deafening vibrations. Now, in these kinds of extreme environments, a split-second safety failure, well, that isn't just a minor glitch. It is a catastrophic, potentially fatal event. So today, in this explainer, we're doing a full teardown of the Apex technology designed specifically to survive and protect in that exact chaos. We're looking at industrial-safe radar systems, specifically digging into the Pilz PSENradar. Now, to really get why this matters, think about the stark contrast here. On one hand, you have traditional optical technology, like your standard laser scanners. And look, in a pristine cleanroom environment, they're great. But what happens when you introduce a massive cloud of thick smoke, a sudden blast of steam, or heavy welding sparks? The light scatters. It completely blinds the sensor. The optical system literally fails. But on the other side of the equation, the radar sensor doesn't just survive all that interference, it pushes right through it. It projects this invisible, pulsing 3D volumetric dome of radio waves, basically just ignoring the chaos entirely. And that brings us to the core takeaway here. Light fails in the dark, the dust, and the smoke. But radar sees everything. It is fundamentally changing the rules of industrial automation safety. We are finally moving away from these fragile, easily broken optical lines and stepping straight into the world of bulletproof active radio wave protection. Section 1. The radar advantage. So, what's the secret sauce? The resilience of this system actually comes down to 4 letters. FMCW. That stands for Frequency Modulated Continuous Wave. Now, this is not just some passive motion detector you'd find in a hallway. This is an active protection radar algorithm. What it does is continuously send out radio pulses, and then it instantly analyzes the reflection of the very nearest moving target it encounters. It's constantly dynamically calculating distance and motion based purely on how those waves bounce back from the physical world. And the sheer engineering precision at play here is just fascinating. These systems operate in a highly specific working band, 24 to 24.25 gigahertz. Working at that specific high frequency is exactly what allows the sensor to effortlessly penetrate all that environmental debris while still maintaining the incredible sensitivity it needs to detect the subtle, tiny movements of a human body entering a dangerous zone. Put that 24 gigahertz FMCW tech into a real-world application, and it means radar is fundamentally immune to massive environmental hazards. We're talking dust, smoke, steam, heavy rain, and intense machine vibrations. Think about it. Any single one of those hazards would instantly trigger a false alarm or completely blind a standard optoelectronic sensor. But the radar? Those radar waves just pass right through them like they aren't even there. Out on the gritty reality of a processing plant floor, you are constantly dealing with a chaotic mix of debris, heavy interference, maybe metallic flakes in the air. If you're running a massive corrugated cardboard plant, a heavy woodworking facility, or a giant metalworking lathe, the air is just thick with particulate matter. Optical sensors? They're going to require constant wiping down and maintenance. But radar just cuts right through the grime. It ensures you have continuous production without sacrificing a single millimeter of operator safety. Section 2. Volumetric 3D monitoring. Now, this is where it gets really cool. By adjusting the sensor's inclination, basically angling it up or down around its x-axis, engineers can project a true 3D volumetric dome. Think about a laser scanner for a second. It essentially shoots a flat 2D plane of light across the floor. If you step over it or crawl under it, you've just bypassed the entire safety system. Radar doesn't work like that at all. You aren't just drawing a line on the ground, you are filling an entire three-dimensional space with invisible protective waves. And engineers can actually shape that 3D dome based on exactly what the environment needs. You typically have 2 main horizontal angular coverages to work with. The 110-degree wide field is absolutely perfect for broad, sweeping coverage of a massive factory floor. But then you have the 50-degree targeted field. This one is engineered specifically for extreme resilience. Let's say you have highly reflective materials around, like heavy water splatters, rain in an outdoor setup, or giant piles of iron shavings. That tighter 50-degree beam cuts directly through that specific interference to prevent spurious alarms while keeping total safety intact. Section 3. Rear Access Protection. Okay, picture a complex robotic welding cell. If you've seen one, you know these multi-axis robots are incredibly fast and totally unforgiving. Inside those safety cages, you've got massive metal fixtures, custom tooling, and huge parts being welded together. All of those physical objects create dark spots, blind spots, places where a human operator doing routine maintenance could be completely hidden from a camera or a laser that's positioned outside the cell. And that brings us to the absolutely terrifying danger of the blind spot. Imagine an operator steps into the cell to clear a jam, and they step back behind the robot. An unaware colleague on the outside hits the reset button, or maybe the machine's logic controller initiates an automatic restart on its own. If the safety system can't see the operator hidden in that blind spot, the heavy machinery restarts, and the consequences of that are fatal. Radar totally solves this nightmare through a really simple active sequence. Because that radar wave bounces all around the area and monitors a full 3D volume, it catches even the subtle motion of a human hidden back in that blind spot. So, step 1, motion is detected, even behind partial obstructions. Step 2, the safety outputs remain securely deactivated. And step 3, the machine is inherently prevented from restarting. The radar literally locks the system down until that entire volume is completely clear.
Section 4, Zone Configuration.
To make all this work in the real world, the radar's field of view is typically split into 2 distinct detection fields. This balances safety with actual production efficiency. Detection field 1 is usually configured as your outer warning zone. If motion is detected there, the system might trigger a warning alarm or command the robot to slow down safely. But detection field 2, that is your protection zone. If a human breaches that inner volume, the system triggers a Category 3 safe hard stop. The machine loses power immediately. It's a beautifully structured escalation, from an early warning straight to absolute protection. Now, let's ground this explainer in some gritty reality for a second. Physics has limits, right? Radar is incredible, but it is not magic. To engineer truly safe systems, you have to respect the absolute boundaries of the technology itself. So what exactly are those limits? Well, first off, radar detects motion. It cannot detect the presence of a person who is completely immobile and literally not breathing. Second, while it actively protects you from the machine moving, it offers zero protection from pieces ejected from the machinery or heavy objects falling from above. And finally, it's vulnerable to masking. If a heavy layer of highly conductive material, like a thick metal plating, were to somehow cover the sensor, it would warp or entirely block its field of view. Engineers always have to validate the system under their exact operational conditions.
But look, even with those physical laws firmly in place, the conclusion here remains totally undeniable. When optoelectronic sensors reach their limits, when they are blinded by smoke, choked by dust, confused by water, radar takes over. It is without a doubt the definitive apex safety technology for the most chaotic and unforgiving industrial environments on Earth.
Which leaves us with one final, pretty provocative thought to wrap this up. Think about the most hazardous, debris-filled automated processes in your own facility right now. Are they truly volumetrically secure, or are you simply crossing your fingers and trusting the light in the dark?